Hello, my name is Marco, and in this video I'm going to explain how to solve a machine learning example of the energy and utilities field using Neural Designer. The topic of this example is solar power generation. A certain company wants to build a solar farm, but its efficiency has strong dependency on the environmental factors of the site. They want to build a model which helps them decide where to place their project. At the end of this video, we will see how, using machine learning techniques, we can predict with small error how much energy we can expect from a solar farm. First, we will download the data file from the link below. If we open it, we will see that it contains information about 2,920 instances, each representing the power generated during a 3-hour period and the ambient variables at that time. The data file is organized in 13 columns: the distance to solar noon in radians, daily average temperature, daily average wind direction, daily average wind speed, sky cover, visibility, humidity, average wind speed for each 3-hour period, average pressure for each 3-hour period, and finally, the target variable, power generated. Now we can open Neural Designer, where we can see two different project types we can create. In this case, we want to make an approximate prediction of the target variable based on the rest. In order to do that, we will use the approximation project functionality. Once we've created the project, we must import the dataset we just downloaded. Once it is imported, we can see a preview of the data, which gives us the number of columns and rows in our file. In this table, we can check the different variables or features and select the one that is going to be the target variable. In this case, we will choose power generated. In order to get to know our data, we will perform a brief analysis. First, we want to know how the different variables are distributed, and in order to do that, we can calculate the column distributions. We have different distribution charts for each variable. At the end, we have the histogram for our target variable. We can see there that most of the samples fall in the first bin, showing an exponential distribution. That is the data we are seeking to model. We can also check which of the variables has a greater impact on the target variable. We can do this by calculating the inputs-target correlation. Here, we can see that the most correlated variable is distance to solar noon. This makes sense, as the closer the sun is to noon, the greater the radiation the solar panels will receive. Now we've reached the time to start building our model to predict the power generated. We will click in the Neural Network tab, where we can alter the network's architecture settings. As a first guess, we will leave everything by default. Now we can create and visualize our neural network. This diagram means that when we introduce 12 inputs or variables into our neural network, it gives back one output. The next step is to train our neural network. That means to search for the weights or parameters that will best fit our data. After the training process, we can see how the error has decreased with each iteration. The most important result is the final selection error. As we chose as metric the normalized square error, a value of 1 would mean that the network predicts in the mean, and an error value of 0 would mean that it makes a perfect prediction. We can see how good the model is by performing several testing analyses. In approximation problems, the best way to visualize the model's performance is to make a regression analysis. In this chart, we can see in the x-axis the real value of the target variable, and in the y-axis the predicted values. If the model was perfect, the regression line would be a straight line with a slope value of 1 and passing through the coordinates origin. In our case, we can see how, even though the regression is not perfect, all the values fall next to the regression line and we have a good correlation coefficient. Another testing method is visualizing the error's histograms. We can see here the distribution of the error values. This figure shows that most of the error values are close to 0. If we calculate the error statistics, we will see that everything makes sense, as the mean percentual error is 7%. This means that our model predicts the power generated by a solar farm with only 7% error. Finally, we can calculate specific outputs in the model deployment section using the calculate outputs function. Here we can see our model's target variable's value for a given set of inputs. Another useful functionality of the model's deployment section is plotting the directional output, where we can see how the target variable depends on the inputs. It is also possible to write our model's mathematical expression or to export it to different programming languages as Python or C. Thanks for watching. Hopefully this video helped you make the most of Neural Designer. Don't forget to subscribe if you liked our content and if you want to learn more about machine learning and Neural Designer.